Okay, I'm going to talk about another interesting situation where the divergence theorem is helpful, and it's when you have odd functions in the divergence itself. Remember what an odd function is. X is the prototypical example of an odd function because it's symmetric about the origin. In other words, it's positive on one side, negative on the other side. It's characterized by, if you reflect it, you get a minus sign. So if you reflect it, you get a minus sign. That's what it means to be odd. So, and x cubed is another example. And odd functions are nice because the integral of an odd function over a symmetric domain is actually 0 because the positive cancels exactly with the negative. So for example, the integral from -1 to 1 of x dx or x cubed dx is actually 0. And you could do that by anti-differentiating, of course. But what's another way to do that without performing the integral? So how do you do this? So rather, how do you show it's equal to 0 without evaluating? Like, what if we had a really bad function and we didn't want to integrate it? So here's how. You do a u sub. So you're going to let x equal minus u and dx equal minus du. So then your integral from -1 to 1 of f of x dx turns into +1 to -1 of f of minus u d minus u. Or rather, I should say minus du. So we end up wanting to switch this to the usual negative to positive. This is equal to minus negative to positive. So we end up with minus f of minus u du. This is, of course, just f of minus u du. Okay, so now let's use the fact that it's odd. So our integral is equal to the minus, we have a minus sign from the odd, property of exactly what we started with. So the only way an integral could be negative itself is if it's 0. So in other words, we just showed that I equals negative I. So that means 2i equals 0. And this is just, if it seems like magic, it's not magic. It has to be true by this geometric interpretation of odd functions over a symmetric domain, right? This is just a mathematical way to express this without computing these integrals. So the reason I'm going back to one-dimensional calculus is because these integrals show up a lot in 3D, and we'll do one example of this. So the problem is to use the divergence theorem to calculate the flux integral f dot ds, where s is the usual sphere, and we'll just do x squared plus y squared plus z squared equals 1, and f is this vector. It'll look like x cubed y, y to the 4th, and z cubed y. So this is kind of a nasty surface integral. You would have to use spherical coordinates. You would get quartic trigonometric polynomials like sine 4th, cosine 4th, sine squared, cosine squared. That would take me, it would certainly take me a good amount of time to do that. But we're going to do it in less than 5 minutes, just by using the fact that the divergence has odd functions and the sphere is symmetric. So the sphere is symmetric, And we'll show that del f, the divergence, is odd. So let's do this. So ddx of x cubed y plus partial derivative of y to the fourth in y plus the partial derivative in z of z cubed y, we end up just getting 3x squared y plus 3y, I'm sorry, I can't do basic chain rule apparently, plus 4y cubed plus 3z squared y. So we're looking for odd functions. Y and y cubed show up in each term. Here's a y, here's a y cubed, and here's another y. So therefore, it's odd in y. And now we do not care what it looks like. All we care about is that it's odd in y. Okay, so now we've shown that our surface integral is equal to this volume integral over the ball of radius 1. And so now it is odd in y dv. Okay, so now notice that, let's just pretend that this is y. This is the y-axis, and this, let's just say this is the z-axis. So notice that we see there should be cancellation on either side of positive y and negative y. So we expect this to be equal to 0. Okay? So how do we show this using math? So here's one way to do it. You write it as a triple integral. So you can write it as an x, y, z triple integral. Okay, so here's how you do this. You put y in the inside. So dy. And let's just for concreteness, I'm going to use one of these terms. We'll do this term, the 3x squared y. 3x squared y dy. And so now we'll have, what are our ranges going to be? Well, it'll be, we have our sphere, right? Really, there's an x too, but I'm just trying to draw to simplify. So we have x squared plus y squared plus z squared equals 1. So if you solve for y, you get y equals plus or minus 1 minus x squared plus z squared. So I'm just going to abbreviate this by minus the square root plus the square root. Okay? Hope you all know what I mean by that. So now we're going to have our dx dz. And I'm going to abbreviate this by the xy, xxz ranges. Really, what are the x and z ranges? It really should just be x squared plus z squared less than or equal to 1, but this is not important. Because we're actually going to show that this inner integral is 0. Okay? So this integral is of the form minus a to plus a of y dy. This has to be 0 because y is an odd function. And if you forgot about that y, let's just go back to my 1D discussion of cancellation. Okay? So if you write it as an iterated integral with y on the inside, you can extract the one-dimensional odd property which kills integrals. And so the three-dimensional complexity is gone. So we overall will conclude it is 0. Okay, I hope this was helpful. Thanks for watching.